titled Thermal Management in Electronic Device with COMSOL. First, let me introduce myself. My name is Kajal Mehra and I'll be moderating this exciting webinar for you. Here now I am elated to welcome our speaker, Dr. Antis K. Martin from COMSOL. To enlighten our attendees about Mr. Martin, he is an applications manager at COMSOL, specializing in CFD and heat transfer. He has a bachelor's degree in mechanical engineering from the SCMS School of Engineering and Technology. He received an MS and a PhD from the Indian Institute of Technology, Madras. For questions, requesting everyone to write their questions in the Q&A segment. Also, we will be conducting polls during this 1-hour webinar, so please share your opinions in the poll box section. We will be providing the information about the presentation on demand after the webinar. You can share your interest to us by writing at info@theworldpost.com. And now, allow me to welcome our esteemed speaker, Dr. Martin, who will be starting the presentation, and also he will be sharing live demonstration during this 1-hour webinar. Dr. Martin, requesting you to share your screen and start the presentation.
Thank you so much, Kajal, for such a wonderful introduction. So I believe that actually my screen is visible. Could you please confirm?
Yes.
So good afternoon, one and all, and welcome to the session, which is actually a nightmare for many of the engineers, including me, which is none other than thermal management of electronic devices. So for many of us, the words thermal management is actually, I would say, it's to the surface, or it is becoming popular because of the battery revolution. But what if I would say that the concept of thermal management was there since the beginning, or even the BC, I would say. I mean, if you look back, the ancient civilization like the Egyptians and Greeks used passive thermal management techniques in architecture. And if you come to the Romans, they developed some kind of Hippocrates system for heating public baths and even the private houses. And I believe that the word chimney is well known. And in the Middle Ages, they have introduced this concept of chimney. And nowadays, actually, it is available even in the form of smart chimneys. So in a precise way, I would say, just like Apple used to fall even before Sir Isaac Newton discovered gravity, the concept of thermal management was there since BC. If you look now, we can see steam engine or some kind of smart devices. And if you look at the electronic devices, even the semiconductor application, the size of this kind of devices are going down, which means for such kind of sophisticated devices, thermal management is actually really important. So without any delay, welcome to the today's session, thermal management in electronic devices with COMSOL Multiphysics. So myself, Antis K. Martin, and I'm looking after CFD and heat transfer in COMSOL. So let us try to make it more interactive. So before going further, I would like to know about your background. So I would like to launch a poll question so that actually you can answer that, and accordingly I will be able to model my presentation. So my question is, I'm currently a regular user of simulation tools, evaluating simulation tools for my ongoing upcoming project, attending the session out of personal interest, new to multiphysics simulation. So you can use this poll question and you can answer it there, or even you can use the chat box if you specifically want to give your answer there. So we will keep it for some seconds. I request everyone to give the response there. So Kajal, I believe that we can keep it for next 20 seconds.
Yes, sure.
Yeah. So I request everyone to give the responses so that actually I will be able to model my presentation accordingly, considering your background, whether you are new or not, including the multiphysics word.
Requesting everyone to please vote.
Okay, thank you so much. So maybe I will go to the core part of the today's session, and I will start with the word, what is multiphysics? So going forward in the coming slides also, we are going to repeat this word multiphysics. And I believe that for many of the people, multiphysics word is very familiar. But I would like to make it clarify that what do you mean by multiphysics? As the name suggests, COMSOL Multiphysics we are focusing on two different things. One is flexibility, another one is accuracy. Flexibility means we are solving this, the numerical equations when it comes to the interfaces. But since we are evolving day by day, you may need to modify the existing equation. So COMSOL is not a black box where you will be able to modify the existing conventional equations, and even you can write your own equation. Now, coming to the word accuracy, we believe that if you really want to capture any real life problem, it is always going to be multi-physics in nature. So let me take a simple example. Just imagine actually you are working with a semiconductor device, and we may experience some kind of, my objective here is to understand, or maybe I am going to work with an EM device. So my objective here is to understand the EM characteristics. Obviously, it's a single physics problem, which deals only with the EM. But we know that majority of the time, due to Joule heating, or maybe I would say in a simple way, electromagnetic heating, there will be some heat generation. And it's really important to understand how much heat is getting generated. So in COMSOL, you can add the same model, same interfaces, or the heat transfer equations to the same model, and you will be able to understand the EM characteristics and the heat generated. Now the fluid dynamics engineer will come. He will ask how much heat is required to carry away the heat from the system. Then you can use the fluid dynamics interfaces, and by using a single model file, that by using a single GUI, you will be able to understand how much heat is getting generated, how much fluid is required, along with the EM characteristics. In this way, you will be able to couple different physics, and you will be able to use the same thing for your real life application. Now you will be wondering whether COMSOL is actually best one for single physics. Obviously, in COMSOL, you can even handle single physics. It could be EM physics or chemical physics, mechanical like CFD and heat transfer, or even the structural and acoustics. On top of that, you can couple the same with any physics like electromagnetic heating, thermal stress, or even thermal expansion. You can go for electrochemical heating, and you will be able to address all of your problem by using a single GUI. So I will explain what you mean by single GUI in this concept, maybe in the coming slide. Till now, we have just introduced about the COMSOL software. Now, many of you will be thinking whether people are using or any kind of user stories or success stories. Definitely yes. So I have collected a couple of user stories just to give an idea how people have been using COMSOL software across the industry and even nowadays in the main academic research and development area. So the first user story is actually something related to the electromagnetic heating. So we know that the power electronics generally appears in many everyday products, including smartphones, electronic car parts, household objects. And it's really important to understand how these devices are performing, whether heat is getting generated or it's going to affect the system. So these things are actually really, really important. On top of that, when it comes to the harsh environment, I'm talking about the temperature ranges, maybe about 225 degree or maybe less than 0 degree. It's really important to understand whether these electronic devices are giving the or performing at the same intensity, or maybe I would say same level of performance. So because of this challenge, the company really want to create an electronic package to survive in this kind of harsh environment. So they approached COMSOL, and with the help of COMSOL, they were able to couple low frequency physics, and they were able to couple heat transfer, and that too by using a live-link product, which is live-link for SolidWorks. With the help of that, they were able to optimize the device geometry, layer thickness, minimize the inductance, and even the thermal resistance. So the major challenge they were facing is to couple these physics simultaneously. At the end of the day, if you are not able to solve all these equations in different physics simultaneously, you may not be able to replicate the real life problem as it is. But with the help of COMSOL, by using the low frequency electromagnetics and heat transfer, along with the live-link for SolidWorks, they were able to optimize, and they were able to create a packaging which actually helped to survive in a harsh conditions and even the extreme temperature condition, which is about 225 to 250 degree Celsius. Now, if you look at the second success story, which is actually from Bosch, I believe that the word itself is actually like a self-explanatory. We believe that Bosch is actually one of the well-known industry in the market right now, especially from the automotive point of view. So their major challenge was to create the DC link capacitors. Ideally, the major problem they were facing is because of the hotspot, and these are actually very sensitive, and it is actually creating too much heat. So the major challenge they were facing is, again, the low frequency physics coupled with heat transfer, and they have coupled the leveling for MATLAB as well. So they approached COMSOL. With the help of COMSOL, they were able to couple all these physics together, and they found that they were able to optimize the design and optimize the inverters have a 6% greater range and even a 200% jump in the power density. So these are actually some of the user stories which are available in COMSOL and which are actually available on the website as well. If I try to explain in detail, definitely it will take more time. So I'm not going to spend time over there. But if you are really interested, we can share this information with you so that actually you can explore more. Till now, we have discussed about the user stories as well. Now, many of you will be thinking, why COMSOL? What about the other softwares? Now, let us try to understand what COMSOL can do when it comes to thermal management. So if you look at the thermal management, the heat could be due to various reasons. It could be due to electromagnetic heating. It could be due to electrochemical heating. It could be due to even some other, maybe radiation or some other sources. So it's really important to understand how heat is getting generated and how much fluid is required to carry away the heat from the system. So this is a typical graphical user interface of COMSOL, where you can see the workflow. So left side, you can see the model builder, where similar to any experimental or any numerical analysis, you need to have a well-defined problem in your hand. Then you can go for the geometric creation. Then you can go for the material selection, boundary conditions, meshing, study, and the results. So everything is going to happen in this GUI. Now, I believe that why I'm always saying a single GUI system. Now, the settings window is just to communicate to COMSOL software. If you really want to put your own values like maybe velocity details, maybe a heat source value, or maybe a outlet condition or outflow condition, then you can make use of the settings window. Right side, you can see the graphics window, which will give you the complete picture about how the simulation or how the pre-processing and even the results and visualization part. One more window is there. We call it as information window, which is actually at the bottom. Will help you to see how the simulation is progressing. How, if you really want to pull out any numerical values like I would say some tables or maybe column, then you can definitely make use of the information window. Top window, we call it as a ribbon window. This is just to create the user-friendly atmosphere. If anyone want to pull out any condition, it could be domain condition, point condition, or even a boundary condition, he can make use of the ribbon windows as well. So in COMSOL, again, by using a single GUI, you will be able to couple all these physics. Now, when it comes to heat transfer, you can go for conjugate heat transfer, you can go for free and forced convection, and on top of that, all the turbulence models are available in COMSOL. Also, you can go for stationary and even the transient study. And while using COMSOL, these are the benefits you are going to get. As the name suggests, it's a multi-physics tool, which will help you to couple all these major physics. On top of that, it will give you the complete flexibility to modify the equations and modify the boundary condition. And we are using a finite element approach. Obviously, the accuracy will be on the higher side, and you will be able to certain parametric optimization to cut down your simulation time, and you will be able to optimize your devices. So these are some of the advantages why to go with COMSOL software. And on top of that, actually, you can do n number of things. You can capture the real life scenario as it is. So when it comes to thermal management, why that heat source, or from where actually the heat source is coming, and how you can do that in COMSOL? Obviously, you can do that in 3 different ways. The first way is user defined. Suppose if you know how much heat is getting generated because of electromagnetic heating or electrochemical heating, then you can use certain empirical formulas, and you can use the same thing by user defined approach. So you can give that explicitly by using the heat source option. Now, the second approach is from other physics. Other physics in the sense, suppose if you are solving for EM physics and you will be able to know the heat generation, you can use the same thing in the heat transfer physics. Obviously, this won't be a bidirectional one. But in real life, what is happening? When you operate any electronic devices or any maybe a battery, we know that the battery will be working and the heat will be generated simultaneously. You cannot run the battery for some period of time. You cannot use the heat source to repeat that in the heat transfer physics. Obviously, you can do that by compromising the accuracy. But in COMSOL, you can do the multi-physics coupling for all the electromagnetic and even the electrochemical heating, which will help you to understand how the heat is getting generated and how the corresponding heat is going to affect the performance of the system, kind of circular dependency. Let us try to understand which all are the inbuilt predefined multiphysics coupling, which will help you to understand the heat generation and corresponding performance. I will start with a microwave heating. I believe that actually the word itself is self-explanatory, which deals with the high frequency. And a classic example is potato in a microwave oven. Now you can go for joule heating. And this word is actually, obviously joule heating is something will come to our mind when you talk about the electromagnetic heating. And again, an example here is bus bar. The similar thing is applicable for inductive heating as well. So here actually you can see a steel billet inductive heating. Similarly, you can go for all kind of thermoelectric effects, and we have conjugate heat transfer to account for the fluid flow and heat transfer. We have thermal expansion. Suppose if you are not able to do the thermal management properly, even after doing the free convection or even the forced convection, sometimes still it will go beyond the considerable temperature range. Then the next thing is the structural damage, which is actually thermal expansion or even the thermal stress. To account for that, you can use the thermal stress in the multiphysics coupling, which is a coupling between heat transfer and structural mechanics. You can go for porous media. Nowadays, each and every electronic devices will be having porous material to absorb the moisture, to absorb the sound and even the vibration. On top of that, there are several applications from the porous media point of view. So we have in COMSOL, we have inbuilt couplings and interfaces for porous media as well. And we have heat and moisture transport. And obviously the word itself is self-explanatory. Because of the heat generation, there will be, and because of that condensation will be there, which may cause further damage to the system. So it's really important to understand the moisture transport as well. So these are some of the predefined coupling which are available in COMSOL. On top of that, actually, we have n number of couplings which are actually predefined, and even you can do it by that manually as well. With this, I would like to know how you are going to, or what kind of application or what kind of heat source you are going to consider. So my second poll question is, I'm interested in modeling electromagnetic heating. It could be anything, joule heating or microwave or even the induction heating, electrochemical heating, thermostructural effects, something beyond that temperature actually went beyond that limit, and even you can specify. So maybe I will keep this poll question maybe for the next 20 to 30 seconds. I request everyone to give answer for this poll question so that actually I will be able to give, or I will be able to concentrate more on those kind of things in the coming slides. So we will keep this poll question maybe for the next 20 to 30 seconds.
Very pleased both to help Mr. Martin to go ahead.
Meanwhile, if you have any queries, definitely you can use the question box and you can share that. So towards the end of this session, we will take that one by one, and we will make sure that all the queries will be answered from our side, either during the session or from the support. So thank you so much. So we'll go to the next part. So till now, we have discussed about the introduction part, some of the success stories, and some of the capabilities from the COMSOL point of view. Now you will be wondering how you can do that in COMSOL, whether this technology is actually kind of a complete package or it's a kind of a customized thing, or do you really need some kind of interfaces or modules to tackle this kind of problems? Definitely yes, but in a precise way, everything will be taken care of by the heat transfer module. So I will explain that in detail. So heat transfer module is actually an add-on to base package, which is mandatory, which I will be showing in the end towards the end of this session. So what are the capabilities of heat transfer module? Definitely conduction, convection, and even the radiation. I believe that there is no surprise because this is possible with majority of the commercial tools available in the market right now. But most of the cases, the properties or maybe some parameters are always anisotropic. You can take any device, it will be always anisotropic in nature. Maybe it is nonlinear also with certain orders. So in COMSOL, these are inbuilt, where you can go for both anisotropic and nonlinear approach directly for any properties. Similarly, majority of the devices will be having certain thermal contact. And most of the people who are familiar in the numerical environment, it is clear that these thermal contacts are numerically highly difficult to model because of the numerical, mesh density and certain criteria. So in COMSOL, we have a special boundary condition, which is thermal contact. So without modeling that explicitly, COMSOL will able to take care of that, and obviously without compromising the accuracy. Now, if you look at certain materials where the aspect ratio is very high, I would say kind of infinite, then modeling that in the numerical environment again is very difficult because of the mesh density and even other complexity. So in COMSOL, we have certain approximations like a thermally thin layer approximation or thermally thick layer approximation, which will help you to reduce the complexity without compromising the accuracy. So the classic example is here where you can see the conduction of this particular example, where you can see the temperature distribution. Similar thing is applicable even in the case of convection. So you can go for both free and forced convection, and you can go for both laminar and turbulent flow. Now, most of the people will be wondering how the material properties will be taken care of by COMSOL, whether the material property will be a constant or it's a function of temperature or even any other parameter. Definitely, when you have a heat transfer and the material properties, especially if you're going to look into the fluids like air, water, the properties will definitely change. So in COMSOL, these are actually inbuilt, and all the material properties are actually a function of temperature or any other parameter, a relevant parameter. Similarly, you can go for radiation as well. So this is actually a classic example of radiation, which their objective was to understand how the temperature distribution is happening inside the room. So inside the room, there will be maybe TV will be there and humans will be there. So the heat will be coming from many devices or even from human body. So their objective here is to understand how you can distribute this temperature. I believe that this inclined to the winter countries. So they found that if you keep a blower nearby to the furnace, you will be able to distribute the temperature inside the room. And when it comes to radiation, especially if your temperature is more than 600 or even the 700, then you can go for surface to ambient radiation, surface to participating media, and even the surface to surface radiation. So these are inbuilt features which are available in COMSOL. Let us try to understand how you can enable the first feature, which is thermal contact. So as I mentioned, the same GUI used here, obviously the graphics part is actually cut here. And you can see the equation. I'm not going to explain the equations in detail, but you can see a special boundary condition, thermal contact, and the thermal contact will be implemented for that particular contact. So now here you don't need to explicitly model that contact. Obviously you can do that and you will be able to do that. But the problem here is once you have this kind of contacts, the mesh density will increase and even the numerical complexity will also increase. To tackle that, to avoid that, you can use certain boundary conditions like this. Similarly, if you look at the high aspect ratio geometry, so this is actually a classic example, and I'm not talking about an aspect ratio of this particular geometry. So here we have a thin film where actually the current is flowing through this film and it is coming through here. So it is going to be the terminal and this is going to be the ground. So our objective here is to understand, because of Joule heating or because of the electromagnetic heating, how the temperature is actually getting distributed here. So again, by using this kind of approximation for thermally thin approximation or thermally thick approximation, you will be able to do that. And nowadays, there is a trend to use composite materials for many of the electronic devices, especially for the casing, to reduce the weight of the entire setup. There also, you can use the same principle and you can go for single layer materials, you can go for multi-layer material, and even the layered material stack. So these are actually some of the capabilities, especially from the heat transfer point of view, that too from the conduction point of view. Till now, we have discussed about this, where the heat is getting generated, how it is going through the surface. Now, how you can remove it from the surface. Let us try to understand the convection part or the heat transfer in fluids. Similar to the conduction, we have n number of examples or n number of options for the heat transfer in fluids as well. So we have certain boundary conditions like a inflow condition and even the outflow condition. And one of the major option is open boundary. Suppose if you are going to do some kind of phenomena inside a room, and obviously inside the room there will be electronic devices to eject the heat, but there will be a window, and sometimes actually the fluid or the heat transfer will happen from outside to inside, or maybe sometimes from the inside to outside. So if you use open boundary, depends upon the physical phenomena, COMSOL will automatically act that particular boundary as an inlet or outlet, which means mass flux is free to come in or come out. Similarly, we have certain boundary conditions like a fan, screen, and I believe that maybe I will explain that in the during the time of demonstration. So fan boundary condition means, suppose if you look at our CPU, we know that inside that there will be an exhaust fan. If you model that numerically in a numerical environment, definitely this will be highly tedious. The reason is, to model the fan geometry itself will be numerically very complicated. But if you use the fan boundary condition, where each and every fan manufacturers will be giving you the pressure data. So if you are able to feed that pressure data in that boundary condition, without modeling that explicitly, you will be able to replicate that fan boundary without compromising the accuracy. Again, you can see the same GUI and same model builder, same workflow is actually used in this particular case also. So let me try to understand the passive cooling, or in a principal way, free convection. In COMSOL, you have the option to account for gravity and even the buoyancy forces by using the Bosnick's approximation. And obviously, this is a classic example of a natural convection. So LED bulb is actually working and it is ejecting some heat amount. And because of the natural convection and because of the buoyancy effect, you can see the fluid is moving up. Obviously, the hot fluid will move up and cold fluid will come down. So you'll be able to account for the free convection. But there are some limitations. For certain application, free convection may not be sufficient. It demands some kind of convection from the force point of view, which is nothing but active cooling, or I would say force convection. In force convection, definitely you can go for all kind of flow conditions, including the turbulent flow, and we have certain boundary conditions as well. So this is actually a classic example of conjugate heat transfer with force convection. I will take this as an example considering certain boundary condition. So here actually you can see thin layer is used. You can see fan boundary condition is used. You can see grill boundary condition is used. If you are going to use this explicitly in any numerical environment, definitely this will increase, the simulation time will increase, the complexity will also increase. But in COMSOL, again by using a single GUI, that too by using this certain specific boundary condition, you will be able to cut down the simulation time drastically without compromising the accuracy. Obviously, this session won't be complete without considering the radiation part. And if the temperature is going beyond 600, which is always a hazardous kind of temperature for any electronic devices, you can definitely account for the radiation effects as well. And as I mentioned, you can go for all kind of radiation. And when it comes to the analysis type part, in COMSOL, you can definitely go for stationary study, transient study, and even the frequency domain study. And there are multiple subcategory options. But from the fluid dynamics or heat transfer point of view, we have stationary and even the transient study. Obviously, there are so many options for rotating machinery, and even for several other options are there. Depends upon the requirements and depends upon the demand of the problem. You can use any of these approaches. And when it comes to solver settings, you don't need to worry about anything, because automatically COMSOL will take care of the best possible solver settings for the possible physics. And we don't need to look into that part as well. Till now, we have discussed about the thermal management, especially from the higher temperature point of view, assuming that the temperature is going up beyond the permissible temperature. What if your temperature is going below the permissible temperature? Just like a winter country application, maybe for a battery vehicle where the temperature is actually very less. So to trigger the electrochemical application, it's mandatory to have a limited or permissible temperature range, similar to a thermostat, or I would say an iron box, where you need to keep your temperature within certain limit, or maybe for a water heater. So in COMSOL, we have certain interfaces like event interface, which will take care of this. So this is actually an example by using the event interface. So our objective here is to keep the device within the temperature of 45 to 55. And the moment it is going beyond 45, the heater will be on and it will go up to 55. The moment it is going beyond 55, it will cut off, similar to a thermostat. So for all this kind of application, definitely you can make use of the interfaces, which are actually event interfaces. And these are actually not like physics-based interfaces. You can use the same thing with any physics. It could be a single physics alone. It could be a multi-physics as well. And let us try to understand how the multi-physics part will take care of the thermal management. So this is actually a classic example of electromagnetic conjugate heat transfer, where you can see a heat sink and the fluid flow is actually happening, and the heat sink is actually dissipating the heat. And as I mentioned, the module requirements are heat transfer module will definitely take care of conduction, convection, and even the radiation, where AC/DC module will take care of the electromagnetic heating. It could be joule heating, induction heating, or even the microwave heating. On top of that, if you really want to account for the electrochemical heating, then you can go for the battery design module. And if your temperature, even after doing all these kind of efforts, if the temperature is still going beyond the permissible, then obviously structural physics is required for the thermal expansion or even the thermal stress. And as I mentioned, these are the studies, stationary and even the time dependent analysis. So non-isothermal flow multiphysics coupling, which is actually we are using for the conjugate heat transfer, where you will be having conduction, convection, and even the fluid flow. So here we will be coupling these together in a circular dependency way, where the temperature properties will be, or the material properties will vary with respect to temperature. Similar thing will be applicable for electromagnetic losses. As I mentioned, the same GUI will be used. So this is actually a classic case of electromagnetic heating. You can see that the same GUI is used here, and you will be able to see the same model builder, same settings window, same graphics window, and even the ribbon window. So by using the same GUI, you will be able to model this kind of problem. Now, if you look at the effects regarding the thermoelectric effects, especially for the refrigeration or maybe CPU coolers from the pelter point of view, or maybe thermoelectric, oh, sorry, I think I just missed it. Yeah. So thermoelectric generators, thermocouples for the Seebeck effect, and from the Thomsons, especially for refrigeration and HVAC application. So these are actually again happening in the same GUI. So you can use the thermoelectric effect coupling here. So in the GUI, you can see the thermoelectric effect. So you can switch from one effect to another by simply changing the options which are available, and these are actually inbuilt in COMSOL. Again, this is going to happen in a single GUI. Now, what if you really want to transfer the heat from one place to another? And obviously, the heat pipes. Heat pipes are highly efficient thermal management devices used to transfer heat from one location to another. And even you can go for porous material, phase change applications. So you will be able to couple fluid flow heat transfer and even the porous media, that too free and porous media as well. And even you can go for the multi-phase flow as well. I mean, like two different fluids. It could be water and air, or maybe some other fluid also. So all these applications can be easily captured by COMSOL, and that too by using the same GUI. Now, if you look at the battery, obviously the thermal management session won't be complete without considering the thermal management of batteries. As I mentioned, for many of us, the word thermal management became very popular because of the battery revolution. Through the social medias and some other news, we are getting this information. Battery got exploded, mobile phone got exploded. So it's really important to understand how you can do that in COMSOL. So obviously, the first principle is lumped, and the accuracy part will be there. And you can go for the heat transfer. And again, by using the same physics, so right now you can see three different physics are actually considered. Fluid part obviously it's removed. So you can see heat transfer, sorry, battery part for the electrochemical part. You can see the heat transfer, and you can see the electrochemical heating coupling. So these are actually inbuilt. And as the name suggests, COMSOL is not a black box. You will be able to see the background equation here. You will be able to understand what exactly happening there. And if you look at the electronic devices or cooling devices, how you can extract the heat from the system. So the first one is actually an enclosure with a fan and grill boundary condition. I mean, you can relate that to our CPU, where you will be having, a fan boundary, or maybe I would say an exposed fan to extract the heat from the system. You can go for certain fins to carry away the heat from the system, like a heat sink. You can go for thermoelectric coolers and even the heat pipes. So these kind of devices are already available in COMSOL, but you can definitely model that from a customized point of view as well. Till now, we have discussed about the heat transfer part, heat generation part, and how you can do the thermal management. But there will be a worst case scenario. Even after doing all these kind of things, you may end up with certain points, or you may end up with certain phenomena where the temperature is going beyond a particular limit. Then what will happen? It's always a question. Thermal management part is clear. We can do the thermal management. We can find the fluid required to carry away the heat from the system. We can do n number of things to keep the temperature within the limit. Suppose if it is going to move above the limit, then comes the importance of thermal stress. Majority of the device will undergo thermal expansion or even thermal stress because of the temperatures. The temperature will increase, which means expansion will happen, will damage the entire system. So you must have seen certain bulgings and other things in electronic devices. It could be due to the thermal stress. So in COMSOL, we have inbuilt coupling for that, and this is actually a classic example of a surface resistor. And our objective here is to understand, suppose if the temperature is going beyond a permissible limit, what will happen, whether any kind of thermal stress or thermal expansion or any deformation or any propagation. So you can even use certain scale-up options to see that visually how it is actually happening. So these are some of the examples which are available in COMSOL and capabilities. I should repeat that word, some of the capabilities which are available. On top of that, n number of things are available, because COMSOL is actually a general purpose tool, but depends upon the application, you can use it for many applications. So we have discussed about the unified workflow or single GUI system. And I would like to show a simple demo also. But most probably I will not be able to show all the physics. So I have collected a couple of slides for that. So the first slide you can see, the slide shows a classic example of pressure acoustics. My objective here is to understand the sound propagation in a simple way, or maybe a sound pressure level, or maybe something like that. Now what if I switch from pressure acoustics to fluid dynamics? Now you can see the same GUI, same interface, and we are just changing the physics and solving our problem. Now what if I introduce battery, or I I remove the fluid dynamics and battery? Now again we are using the same GUI. There is no difference. So if you look from the user point of view, this will be very useful, and this will make the life of the engineers very easy, irrespective of the physics. It could be single physics or multi-physics. At the end of the day, you are going to do the same thing in a single GUI system. So let me go back to the first slide, the pressure acoustic slide, or I would say the acoustics physics, fluid dynamics physics, and even the battery physics. So in this way, you will be able to understand how the physics is actually very relevant and how this physics can be used to tackle problems in COMSOL. With this, I will go to my demonstration. Definitely, I will take one simple example. I don't think I will get time from the scratch level, but still I will open the interface there. Yes. So the moment, obviously, before setting up the problem, you need to have a well-defined problem in your hand. Just imagine I'm going to model the CPU of our computer, where you will be having conduction, convection, fluid flow, and a fan will be there, a grill will be there, and maybe certain high aspect ratio geometry will be there. Let us try to model that problem. So the moment I click on the COMSOL icon, I will get a window like this. Model wizard and blank model. Blank model is recommended for experienced users. Definitely I can use it because I'm using the COMSOL for the last some good number of years. So definitely I can use it. But people like very new to COMSOL, they can start with a model wizard. Now COMSOL will ask you which kind of space dimension. So we have 3D, even 0D, and which is actually for kind of a perfectly mixed system. So I will start with a 3D. Now forget about this recently used. This is actually for me because I was using the COMSOL software. You will get an option from AC/DC to mathematics. And if you are not sure about the interfaces, you can read this message from COMSOL to confirm that you are moving in the right direction. Looking at my problem statement, at the moment, I'm not interested in modeling the electromagnetic heating. I'm going to assume the heat source, and I'm going to calculate the heat source empirically. So what I will do, I will go to heat transfer, and we have a predefined multiphysics coupling for conjugate heat transfer. I will expand conjugate heat transfer, and just imagine my problem is laminar in nature. I can read this message from COMSOL to confirm that I'm moving in the right direction. Now I'll click on the Add button. Here comes the beauty of COMSOL software. The moment you click on the Add button, you got the two possible interfaces, which is heat transfer in solids and fluids to account for conduction and convection, and we have laminar flow and the multiphysics coupling. Now I'll go to study. I will select stationary study. Definitely you can go for transient. You have a number of, you have the, description from COMSOL to make sure that you are moving in the right direction. I will click on the done button. Hope you are able to recall the interfaces which we discussed when I was going through the PPT, or I would say the slides. So the left side again, model builder, settings window to communicate to COMSOL software. We have graphics window where you will be able to see the geometry, mesh, and the results. Information window will help you to understand how the simulation is progressing. You will be able to see the log file as well. And we have ribbon window to create the user-friendly atmosphere. So right now, I'm not going to create it from the scratch. So I will open the same GUI in the COMSOL window, which I have already solved. The simulation time was in the order of minutes. Something in the order of 19 minutes. So I don't want to run it again. So let us start with the definition. So right now, I'm going to assume that I have a well-defined problem in my hand. Now my second step is to create the geometry or import the geometry. So I have imported this geometry, and you can see the import option, and the geometry is actually available. So this is the geometry. So for a better visualization, I will hide one or two boundaries. Yes. Just imagine this is our CPU, and we have a fan here. We have certain maybe devices inside to generate the heat. We have certain fins to carry away the heat, or maybe some high aspect ratio geometries here. So second part is also done. Now we need to assign the material. So in COMSOL, we have 15,000 material, 15,000 plus material with all the relevant properties. That to a function of temperature or any other parameter. So you can select these properties, and you can assign these materials to each domain. So you can see air is assigned for the domain 1, which is the enclosure. We have plastic here. We have steel here, aluminum, copper, silicon, heat sink, which is actually our high aspect ratio geometric part, copper layers, and even circuit board. So these are actually the materials I'm going to consider here. And obviously, these materials are selected from the material library. Now you can see how the material is actually a function of temperature. Now the first physics is heat transfer in solids and fluids, where we have solid domain, which is a default domain. We have fluid domain here. Then we are going to solve with the temperature as the initial condition. So I'm going to use the ambient temperature. By default, all the boundaries will be thermally insulated. And I'm going to give the heat source explicitly. So you can right click at heat transfer, and you can select the heat source. So heat source 1 is actually 25 watt, and the transformer coil 5 watt. Again, different heat sources are there. So I'm using the same node, and I've selected different domain condition here. So these are the options available. You can give different heat sources. Now I'm going to give an inflow condition. So this is my inflow condition where the fluid is going to come in. So you can go to right click at heat transfer, flow condition, inflow. Now you can go to outflow. And at the outflow, you can see the fan boundary condition is selected, assuming that actually the fluid is going to come out of that. Obviously, fan boundary condition I will show you. And for the thin layer approximation, we are using thin layer. You can specify whether it is going to be a single layer or multi-layer. All those information can be given here. Now for the Navier-Stokes continuity equation, or for the flow equation, we have selected one, and we have compressible flow, and we have fan boundary condition. As the name suggests, instead of modeling that explicitly, you can use the fan boundary condition, and you can use the pressure data. Each and every fan manufacturers will be giving you the pressure data. So you can feed that here by using the options here, and automatically COMSOL will act like that particular data without compromising the particular fan, without compromising the accuracy. Similarly, you can give grill condition. So the backside is actually a grill. You can see that in the CPU as well, and you can give the coefficient as well, the loss coefficient. And both are coupled by using the multiphysics coupling, where you will be able to see the coupling, heat transfer and fluid flow. And you can go for the meshing. which is inbuilt in COMSOL. You don't need to do anything. So we have physics control mesh and even the user control mesh. Now you can go for the study. So I'm not going to click on the compute button. I will show you the results. So depends upon the dependent variable, you will get temperature. So you can see the temperature distribution. So I have created with the streamlines as well. You can go for the velocity. You can go for the pressure distribution. You can go for the wall resolution. You can even go with the temperature and fluid flow. So these are the options which are available in COMSOL. These are default. On top of that, whatever things which can be extracted from this simulation can be extracted by using the replace expression option. Everything will be available here. Depends upon the problem statement, depends upon the requirement, you can pull out this. So we are slightly running out of time, so I'm going back to the PPT. So with this, actually, I would like to ask one more question. So after this session, I would like to connect with the COMSOL representative, try out COMSOL for my project, both of the above or none of the above. So I request everyone to give answer for this poll question so that actually my colleague will be able to in touch with you and will be helping you by sharing some relevant resources and even the COMSOL trial license as well. I'll keep this maybe for the next 10 to 20 seconds. After that, actually, I have one more slide, which actually really important, at least for me, because many of you will be thinking about the complete structure of COMSOL software, how you can do this, whether it's a complete package or a kind of customized tool. Definitely yes. So maybe for the next 10 seconds, we will wait for the next 10 seconds and we'll directly jump into that slide.
Everyone, please vote from your side.
So meanwhile, if you have any queries, definitely you can use the question box, and we will, immediately after this slide, we'll start answering the questions. Definitely, I will try to answer as much as I can. On top of that, actually, we will revert back to you from the support as well. So thank you so much, and maybe I will go to the next slide, which is my final slide. So COMSOL structure is like this. So left side, you can see a blue color, which is actually dark blue color, which is the backbone of COMSOL software, which we generally call it as base package. With the help of base package, you will be able to address almost all kind of linear problems, like in the case of heat transfer through conduction and convection, single phase flow, linear electrostatics, linear structural mechanics, and all kind of pre-processing, even the results and visualization, including the meshing as well. For that, base package is mandatory, where the parent codes are actually running. Now we have specialized interfaces for the in-depth research work, which are actually electromagnetics interfaces. We have fluid and heat. We have structural and acoustics, and even the chemical. On top of that, we have multi-purpose module also. All kind of optimization like a parameter, shape, or topology. You can go for optimization module. Uncertainty quantification. Material library. We have around 15,000 material. Particle tracing to see how the particles are actually moving. And we have liquid and gas properties. Similarly, we have live-link products. I have explicitly mentioned about live-link during the time of success stories. So live-link means it's a kind of a bidirectional coupling between COMSOL and the other software. So you'll be able to establish a bidirectional coupling for exchanging the data. Irrespective of this requirement, you need to have the base package, and you can couple any of these physics with other physics or even with your own equation-based modeling. So that's all from my side. And I believe that actually session was helpful for your application. Let me know if you have any queries. So you can use the question box and I can definitely answer that questions.
Thank you very much, Dr. Martin. I hope that you all enjoyed this amazing presentation during the webinar and you take back home a lot of neat information regarding the subject of the webinar. Now, I open the floor for Q&A for our attendees. So here is the one question that is, how do I verify the energy balance for my thermal model? Dr. Martin, I would like you to request you to answer the question.
Yes. And honestly speaking, actually, I was expecting this question because the people who are doing the numerical work, definitely they will ask this question. So in COMSOL, we have a block for that. Definitely at the end of the day, you need to do this and you need to verify that actually whether the energy balance is happening or not. So we can definitely share this link with you. So it's a blog which is actually available in the it is kind of open source blog. You can definitely refer this, where you can calculate or where you can go for the energy balance.
Moving to the next question, what is the difference between the lumped and distributed approach for convective heat transfer?
Basically, the difference and lumped, I mean, I believe that as the name suggests, you are going to assume it's uniformly distributed and there won't be any change with respect to space. At the end of the day, properties are going to be like, I mean, average property. When you go for such kind of assumptions, definitely there will be some kind of compromise in the accuracy. But if you are going to consider that as an actual system, then that is the case, means you are going to replicate the real life scenario as it is. So this is the main difference. But certain problems you can assume that actually the lumped approach is the best approach. I can give you a simple example. Suppose you are going to model the same CPU, and we know that actually radiation effects are kind of negligible. So now it's your choice whether to consider the radiation or not. Even if you consider the radiation, the I mean the accuracy level will not be that affected. So it's up to you, and even it's up to the problem statement. You can assume whether it's going to be lumped or kind of distributed approach.
Thank you. Another question is there a way to ascertain if radiative heat transfer is dominant?
Okay. Yeah, even for radiation, we have, as the name suggests, definitely you can do that. And even there also we have a, I mean, blog. Let me see that. Why I'm suggesting blog, the reason is actually blog will give you the complete picture. So here also you can go for the, and we have a number of radiation interfaces. And on top of that, actually, as the name suggests, in COMSOL, you can go for radiation, that to surface to ambient, surface to participating media, and even the surface to surface. So you can definitely use that, and these interfaces will be really useful. And even these blocks will be useful.
Okay. Next question is how do I incorporate temperature dependent material properties in my model?
Okay, so let me take this example, and I would like to go to the material. And if I click on the air, so you can see dynamic viscosity, thermal conductivity, gas constant, and even the heat capacity. All are actually a function of temperature, obviously not the specific heat gas constant. So you can see the eta value. So maybe I will go to the material properties and I will expand this. So you can see the eta. So now you can see how the dynamic viscosity is varying with respect to temperature. So starting with the 200 Kelvin, it's varying with respect to temperature in this way. Similarly, Cp value also, you can see that it's varying, and even you can see density. These are actually important from the heat transfer and fluid dynamics point of view. So in this way, COMSOL will be able to account for all the possible material and its corresponding influence. And you can even write your own material in the same way. You can use the kind of piecewise function or analytical function to see how the properties are actually varying with respect to temperature or any relevant parameters. Maybe even it could be a space also. Maybe in the x direction it will be varying like this. In the y direction it will be varying in a different way. So you can add that as well. So in this way, you can account for the effective material properties by principle.
Okay, moving ahead to the next question. How do I obtain a heat transfer coefficient for the convective heat flux condition?
Okay, so convective heat flux. I mean, generally in the numerical environment, for the engineering environment, if you are going to give a natural convection over the boundary, I used to prefer 5 watt per meter square Kelvin, which is actually considered as a natural convection. On top of that, if you go to heat transfer in solids here, and maybe I will add that. Maybe I will select heat flux here. Maybe just imagine the heat flux is going to happen here. And right now it is general inward heat flux, where you are actually going to give the heat to the system. If I change this to convective heat flux, now you can see the equation Q equal to HA delta T, and you can give the heat transfer coefficient here. So suppose if it's a natural convection, you can use 5. Obviously, it may not be 5, depends upon the problem statement, depends upon the physical phenomena, maybe location, everything will depends. But in a precise way, or maybe by an average way, In the engineering world, we can use 5 watt per meter square Kelvin as the H value. On top of that, you can change this to convective, change this to external natural convection, and you can specify the value, the L value, how much is actually is exposed to atmosphere. You can change this to internal. You can go for external force convection and even the internal force convection. So in this way, you will be able to account for the H value in a simple way, the heat transfer coefficient values.
Thank you. So due to the lack of time, I'm so sorry, I won't be able to ask all the questions right now. So, however, after the webinar, I will send all the questions to Dr. Martin and request his responses. And with this announcement, I'm going to ask the last question today. In order to model vapor chambers, can we use the multi-purpose optimization for heat pipes, or we can do it in heat transfer module?
Okay, so vaporization, obviously that problem requires more explanation. But from the general point of view, vaporization means there will be a phase change. So, obviously the liquid will become gas, and which demands actually multi-phase simulation. Means you will be having different phases, and even the phase change. Phase change means solid to liquid or liquid to gas. In this case, it is liquid to gas. Now, coming to the word optimization. So if you are interested in the parameter optimization, could be any parameter, or if you are interested in the shape optimization or maybe a topology optimization, then the optimization module will be really useful, and heat transfer interface is also required. So in a crisp way, you need heat transfer interfaces for both porous media and even for the conduction and convection. You need a fluid flow. It could be laminar or turbulent flow. And on top of that, actually, you need to have the optimization. So if you go to the file menu in this interface, you can see in the window, file menu, you can go to application libraries. These are nothing but tutorials which are actually approved and verified. So you can go to optimization module. So let me go to the optimization module. The screen is slightly away from my side, so slightly difficult to understand. Okay, fine. Yeah, so you can see parameter estimation, shape optimization, topology optimization. So you can select any of this, and in this we have a classic example of topology optimization of water, heat exchanger. I think it is not listed here. Definitely we can share maybe after the session. So it's a topology optimization of shell and tube heat exchanger. Obviously vaporization part was not considered, but I think that will be a great starting point for you, where you will be able to see the PDF document and even the model file. So maybe after the session, I can definitely share.
Okay. Thank you again, Dr. Martin, for answering every question and for the great presentation. It was a pleasure to have you with us. So this concludes the webinar. Thank you all for attending. We hope you have bagged the information and enjoyed the presentation. We love your feedback, so don't miss to share your queries and feedback to the whole post.
Thank you so much, the team as well, for giving such a great opportunity. Special thanks to Kajal as well for hosting this session. So once again, thank you so much for your time, and I believe that actually session was useful. And if you have any queries, just feel free to ask the same thing through question box. Right now, it's not available. And you can even try to support@comsol.com so that actually it will directly come to me, and I can definitely answer your queries with the relevant resources. So once again, thank you so much, and have a nice day.
And thanks a lot to all the attendees again.